Okay. 1, 2, 3, that's good. All right, so if you remember, we kind of started talking about control flow integrity and control flow attestation. Generally what we kind of started was like, okay, we have this memory corruption issues. We need to kind of figure out a way to fix these issues, right? And we started with talking about, various different scenarios that we need to do some status checking. We also need to kind of like checking the integrity of the control flow. And then later on, we're going to also talk about kind of like how to isolate to completely kind of get rid of this memory corruption so that our system can still work reliably even in the presence of these corruptions. And we give you an example, and then we start talking about kind of like what we can do, and then that's where we start the idea of shadow stacking. Okay. And then we told you there's a backward edge and a forward edge. There's this control flow graph that probably if you're working with your computer assignments, you have learned about this and you're kind of getting good at it. And we talked a little bit about shadow stack last time. We said that there is a forward edge when we are actually moving forward in your control flow graph, and this is usually some form of a call or a function pointer jumps or virtual calls. And in order to fix this, we usually use CFI. The idea of CFI was kind of pinpointing what are the possible locations of a call, right? And then kind of limiting the system to only go to those specific places. And then like there were a whole bunch of questions, including how do we enforce this? How do we even find all the transitions? What's the overhead? And what I said was that essentially this is what we're going to discuss in the paper presentations that's going to happen on Wednesday. So this is something that you're going to learn a little bit more on Wednesday. Then we also start talking about backward edges, and this is where we talked about the issue of return. The first thing we said that is kind of some sort of CFI wouldn't work. The reason for this is that there are many possible targets for a return, and as a result, you cannot really apply any sort of CFI. Instead, what you should do is that you kind of like check the integrity of that return address. What's the best way to do this? The best way to do this is using some form of a shadow stack, because what shadow stack does is that even if you have a stack canary, you still cannot really provide security for the system because the adversary can kind of like jump over the stack canary or read the stack canary. But there's no way that the adversary can actually kind of attack and corrupt a shadow stack. This kind of like the shadow stack idea was kind of like this, that we essentially like pop and push, like whenever we have a call, we push the address not only into the regular stack, but also in the shadow stack. And when we are popping, we compare the address that's stored in the shadow stack and the address that's stored in the regular stack. There were two different ways of storing shadow stack. One was like you always like store it with some offset to the original stack. The problem with that was that, it's kind of static. So it's kind of like it had lots of storage overhead. But the nice thing about it was that it's very quick because you always kind of like whatever address you have, you add an offset to it, and then you will have the address in the shadow stack. Alternative idea was the indirect mapping, which you usually use a register or another address in the memory to kind of first find what is the base address of the shadow stack, and then everything would be an offset to that. And we said that essentially the second option is more favorable because it's much faster in terms of it's fast enough and it's much more dense. It's much more area efficient. So that's usually people use. In order to do that, you can use a general purpose register, essentially reserve a register as the pointer to the shadow stack. Same way that we have a reserve register as a pointer to the original stack. So that was kind of like mostly it for the shadow stacking. We talk about some things like stack unwinding and so on and so forth. And that was basically it for shadow stacking. Then we kind of switch gear, and it's kind of like the last part of the previous week's lecture, that we start talking about remote attestation, and this is what we're going to use in your computer assignment 4 as well. So I'm going to go through this today, hopefully, and we can finish it, and we can talk a little bit about the computer assignments as well. Also have a little bit of description of what you should do for your paper summaries. So any questions so far? You're good? All right. So remote attestation, if you remember, was the status checking of a remote device. So as I said, this is not a prevention, it's more of a detection scenario. As in like, oh, okay, if they don't want to have control flow integrity or shadow stacking or all those things because they come with runtime overhead. At the very least, what I can do is checking whether or not my device is compromised. How do I do that? I check the status of the memory, and I kind of send a report of that to the remote user. And the remote user can basically check whether or not the device has been compromised. Okay. So any sort of new malware that's been installed in the system, any change to the memory content in the remote device will be detected using remote attestation. And then the remote user can decide, like, the verifier can decide how frequent this request can be. It could be as frequent as every every minute, every hour. And obviously, if you do it more often, there will be more overhead added to the system. This is kind of like the main kind of like high level idea of how remote attestation works. There are essentially two players, the prover and the verifier. The prover is the device under the test, the device in question. The verifier is the ones that we trust, and it kind of verifies the behavior of the system. And the attestation protocol is kind of like a series of messages that being sent and received by the prover and verifier. And there is some measurement process going on the prover in order to kind of find the device. Okay, so yeah. Prover in question or verifier in question? Prover in question. Yeah. So prover wants to prove, verifier wants to verify. Yeah. So you trust the verifier, and then the prover is the remote. Think about it as like, you have a robot or a drone that's kind of moving around. You want to check whether that robot is doing fine or not. We call that a prover, and the verifier is, for example, you or your device that wants to check the status of that device. So what we need to do, fundamentally what needs to be done is that the prover needs to show that the content of their memory is the same thing as before, right? So essentially they need to show that no new code has been installed, or if it is installed, in fact, it's been authorized by the entity, by the centralized entity, the verifier, or any other trusted entity that we have in the system. Okay, so how do we do that? If you remember when we were talking about integrity of data, we said that essentially you can use, message authentication codes and hashes in order to kind of confirm an integrity of something. So usually what we do is we compute the hash over the entire content of the memory, or the parts that we want to make sure that it's not been modified. We send this hash, we can sign it or send it a hash individually. We're going to talk about that actually in this lecture. And then the verifier also independently computes the hash over the content that it has, or it already knows what that value should be, because this is they know what the content of the memory should be, so they know the correct answer. So they compare the answers sent by the prover and their own locally computed answer. If these two matches, it means that the content is the same as before, so we can trust this device. Okay, so that's kind of like the basic idea of what needs to be done in remote attestation. But of course, there's a whole bunch of important assumptions that we need to make, because this process, yes, if this process follows exactly as I explained, then I can trust this device. But the whole thing about remote attestation is that you have to assume that the device is already compromised, and you want to build a system that is robust against an adversary. So if the adversary wants to play this game and lie about their status, our solution should be such that it can easily detect, right? So we should design a system that nobody can kind of cheat in the game, Okay. If somebody tries to cheat, we should be able to detect the cheat. Okay, that's the goal of the system. As a result, the process is not as simple as I described. We need to kind of like, first of all, identify the cheating based scenarios and then come up with solutions to kind of like, eliminate those cheating scenarios. Okay, either eliminate them or at the very least, again, detect that they're cheating, because detection of cheating is also means that the system is complex, right? So we either need to make sure that if the answer is correct or not, if it's not correct, whether it has been truthfully computed or not. Okay. So we start talking about like what are the attack scenarios, and I kind of gave you some examples. And this is one thing that you're gonna do in your computer assignments as well. That you're gonna implement some form of attacks. If you remember, like kind of like this fairly complex picture that I showed you here. One that I told you about is that if there's some part of the memory that's kind of free, it's zeros or not being used, the attacker can essentially change things and remember the things that has been changed and store them into that free part of the memory. Then when it comes for the remote attestation, they can remove their modified code, they can hide themselves, and then recompute the correct hash function or the correct hash value based on those values that's been stored. And then once the attestation has been passed, they can retake over the device again and then kind of continues their malicious behavior again. So that's kind of like the idea. Yeah.
Instead of like storing away the code and then re-verifying the entire thing, can't you just like keep track of the points where the code is done and then just verify up to that point and then start verifying zeros afterwards? Or is that the same thing?
What's the difference? Say it again.
So what you said is that you have to like take your code and hide it versus if you just knew the point at which the code stopped, the like verifier's code stopped, you could just like start with that and then append zeros until the end versus like resetting everything back down.
So let's say that this is the code, okay? Right. And then let's say this part of the memory is free, okay? So the adversary wants to change something, okay? And that change, we are saying that it's going to be somewhere here. So like this part of the memory needs to be changed, okay? So since I'm changing this, I need to first kind of like copy this part here. Then I change it and then use it. So basically this is the malicious code that I'm talking about. And then when the attestation comes, if I compute the hash over this change part, obviously the hash would be different, right? So what I need to do is that I need to kind of revert the process. I need to basically copy this back to here. So basically I need to remove this number one, then copy this back so that this becomes the original one. And then I need to start the computing the attestation, right? Okay. So what was your suggestion?
My misunderstanding was that I thought the code that we wanted to run was in the zeros and like part of the zeros.
Oh, so I mean, yes, of course. If you want to just inject something, so what you're saying, I think, is this, that you have your code here, you have your free zone here, and then you want to modify some of these free zones.
Yeah.
Okay, so in that case, that would be great, because then all you need to do is that you don't need to remove anything. Once it goes to this place, you say that, okay, from this moment on, I'm just gonna send zeros out. Still, so the whole point here is that you need to do some form of a check. So you need some preparation. So for example, in this case here, you need some preparation. You need to kind of remove this and copy this. In this case, you don't need much preparation because you don't need to move around things. But in both cases, you need some form of a checking, right? So you need to, like, for example, here you say that, oh, if I want to read this address, first address, I need to basically, instead of reading the actual content of memory, I need to replace it with all zeros. Right? They kind of need to do some form of a dynamic behavior. And as I'm going to show you later on in this lecture, that's actually what makes it difficult for the adversary, and that's how we can detect it essentially, because there's extra activity that the adversary needs to do, and that could cause some signatures that we can detect. All right. So the attacking scenarios, that's kind of like the two things that the adversary can do. Obviously, the attacker can forge, right? Which means that indeed the content has been changed, but they kind of like, cheat in a way that they produce the correct results. And we call this forging. There are many, many types of forging. And of course, there is replaying, which means that the adversary does not really compute the hash. It just pre-compute the hash and has the hash somewhere. When the request comes, they just forward it. And we said that essentially this can be solved using nonsense, right? By randomizing the answer and making sure no two answers are exactly the same, we are eliminating the chance of pre-computing the answer. Okay, so we kind of like can fix this second issue similar way that we are fixing it in crypto systems. But this first one requires a little bit more work. Okay, so let's talk about that. So as I said, replay attacks, we use a nonce. Essentially, the attack, the attestation becomes a challenge response paradigm, the same way that we described it before. You need to create a randomized input first. You wait for the prover to prove, to send a response. The verifier check that. So, but the only problem with this is that now the verifier also needs to recompute and the hash every time that it sends the request. Okay. In the past, if it didn't have a nonce, the verifier always had one answer, and they can just always compare the two answers together. But now that we have a nonce, now the verifier also needs to go through the attestation process themselves. So they need to compute themselves. But the only difference is that the verifier is trusted, so they always come up with the correct answer. So that's kind of like the downside of having a nonce. And of course, there's a whole bunch of other things such as, how do we actually kind of make sure that a nonce is indeed unique and all those things. But this is very similar to the problems that we have in any other crypto system, that we always need to make sure that the nonce is unique. Then we need to now talk about forging. And the key idea in forging is basically these things that I'm showing you at the end. That essentially, in order to make sure that the forging is not possible, we use this fundamental idea that we not only just look at the response, and in other words, we check that whether the response provided by the prover is the same as the expected response, but we also need some evidence that the calculation is indeed happening correct. Okay, so this second thing is there in order to make sure that the adversary indeed computes the hash correctly. Okay, it's not cheating in this game. It's not forwarding things. It's not moving things around. It's not replacing like the code with zeros and all these tricks that we talk about. If you have some evidence that says that, okay, the attestation process goes exactly as was expected, which is like we read every line of address one by one, we feed it into this hash computing function and so on and so forth. If we indeed do that, then we are good to go. Okay. And as I said, this needs to be designed such that even if the adversary has full control over the system, still we can provide this evidence with some level of confidence. That's kind of the trick that you need to figure out. Okay. So how do we do that? There are generally three common solutions. Okay. The first one is using the hardware. So essentially, if I compute the attestation process purely in hardware, and as long as I trust my hardware, I can say that, okay, this process is working correctly, right? So like, for example, let's say I have my CPU. I may not trust my CPU, but let's say I have something like TPM, like a trusted execution engine or something, okay? If the attestation process happens here, and I know for a fact that this hardware and whatever activity happens within this hardware is not modified and cannot be changed or impacted by the adversary, then whatever is produced from here, I can trust, okay? So if I can trust that, then I can say that, okay, if this answer is indeed the correct answer, then I can trust the system, okay? So this is purely hardware-based solutions, and it's actually very popular solutions being used in many, many systems. But the only problem is that you need to have a dedicated hardware, and you need to this hardware is kind of quite heavy because it needs to be completely independent from the CPU that you have. Okay, so you need isolations and all those things. We're going to talk about this is actually in your module, in the last module of this class, in module 10, when we were talking about like trusted execution environments and TPMs and so on. But for now, we're going to talk about these other two methods that, let's say I don't have a dedicated hardware engine for computing the attestation. Can I still do something with the existing systems? Or maybe I can add a tiny bit of like hardware here, not as big as this, but maybe like a few small modules. And then combination of this untrusted CPU and the trusted hardware engine could provide this correct evidence, that this indeed has not been modified. And this is what we usually call hybrid. The reason that it's hybrid is because it's a combination of software and hardware together. Okay, so let's talk about these two solutions and see what are their advantages and disadvantages and why it's important for us. So as I said, remote attestation using TPM, first thing I said is important. And if you remember, we talked about TPMs, and we said that TPM was this unit that helps us with secure booting, right? So at the beginning, we trust TPM and we build the trust off of TPM for other units, all right? But it was only used at that time for booting. We didn't use it during the actual computation. What we are proposing here is that you can actually use it for actual computation. And as I said, this is the idea of what we call a trusted execution environment. Essentially, we are extending TPM to run dynamic code. And as I said, we're going to get back to this next week when we are talking about trusted execution environments. Just remember that there exists a solution for this. But the problem with, as I said, the problem with extending TPM is that it's not straightforward because of the overhead, especially the hardware and area overhead. And for many, many low-end devices that doesn't really have that much computational power, it may not make sense to have like a dedicated security engine for doing remote attestation. As a result, you want to kind of come up with like these low-cost but yet secure methods. That's what we are looking for in the systems. All right. So the first thing we're going to do is what we call a software attestation. The idea of software attestation is that I don't trust anything in the system except the like tiny bit of piece of software. Can I do something with that? And can I use additional information in order to kind of make sure that the system works? Okay. So let's see how it works. So this software attestation, you can think about it as like, a sequence of software within this prover device. Again, prover is the device that we want to establish a trust on it, okay? What we're going to do is that we're going to say that my software attestation is essentially has two types of code. There is like one piece of code that we call the verification code. This is just, think about it as just one function or one application. And you have many, many other applications in your system. This is just your regular applications. It could be one, it could be many, okay? And what we're going to do is that we're going to design this verification code such that if we follow the steps within that verification code, then we can actually make sure that the system is not compromised. And if you remember, the attestation protocol was basically this, that the verifier sends a nonce and one, it expects to receive a hash of the memory, which also includes nonce, right? So this is what we're going to receive from the prover, okay? So how do we gonna do this? Basically, we're gonna use this main idea that we're gonna use the time it takes to compute this result as basically the information in order to make sure that the process indeed has been followed correctly, okay? So what we're going to do is that we're going to send our challenge, which is essentially our nonce. We're going to wait for the verification code to run the attestation protocol. And if you remember, the attestation protocol was going through every line and computing the hash. what we're going to do is that we're going to make this important assumption that if the adversary doing anything but just doing the hash computation, they're going to incur some time overhead. So if this is t, it's going to be t plus some t1, okay? And then once they send back the results, we're going to time this process, that the time from sending a request to receiving the hash, okay? And we're going to see that this time should be smaller than some threshold, okay? Some known time. So for example, we are expecting that every memory read, for example, takes 1 millisecond or whatever, every hash computation takes 1 millisecond if it's running correctly. So for example, if you're reading 100 of them, it should take, I don't know, 200 milliseconds for computing the hash over 100 lines of memory, okay? So I'm expecting that this value should be smaller than 200 milliseconds, plus or minus maybe some little bit of noise, because this process may not be as deterministic, okay? So I need to design this protocol such that if the adversary incurs, like if the adversary tries to do something else, that would result in some non-negligible time, maybe like, I don't know, like 10 milliseconds at least or more, such that if the time it takes for, computing the response would be something like 210 milliseconds or something, which obviously much bigger than the 200 milliseconds that I have here. And if I can do that, and if I can design my system such that, first of all, I can, measure the time correctly, and second of all, if the adversary wants to try something, they incur a large overhead, then this system will work, because essentially this time is this extra evidence that the attestation has been followed correct. Does that make sense? Any questions? All right, and then the additional thing that we're gonna do is that we're gonna not only just hash, compute the hash over this, we're gonna compute the hash over everything else and then send that. So let me talk about that actually. So this is what we call a self-checking method, okay? So we want to check whether the content of the memory here has been compromised or not, right? So we want to see whether this content, the hash of this memory, is the same as expected hash. So what I can do, option number one, is that I go through every line of memory and I compute the hash, okay? This is a fairly time-consuming process. It may not be as easy that we think it is. So instead, what we can do is that we can do this thing. We can say that, okay, if I send a hash request, I'm going to execute this verification code, this part of the memory, okay? This part of the memory. So what I'm going to do is that I'm going to compute the hash over my own content of memory. Essentially, the idea is what we call a self-checking code, that instead of checking everything, we check ourselves first. That, in other words, the verification code checks itself first, and then send the hash of itself. So this is the piece of code that goes through its own content of memory and compute the hash. And what it does is that it sends this hash value to the verifier. The verifier now can verify whether this content has been compromised or not. If they can verify that, it means that this verifier function itself can be trusted. So in other words, I trust this. Once I trust this, then I can, within this function, then I can compute the hash of the others, and I don't need to time those, because essentially at this point, I trust this already. I don't need to kind of check this one and this one. This function can basically compute the hash itself without sending it to the remote user. Okay? Yeah.
So how did we, can you repeat the question? How did you get across the time challenge?
Yes. Let me actually draw it here. So my memory is like this, okay? So I have my verification code. This is the code for the actual attestation, okay? So it's like, oh, get the response, like get the nonce, go over the memory line by one, hash function computation, and all those things. This is the code for that, okay? But this itself, the attestation process, is, think about it as a program, right? It says like line of codes, okay? This is residing in both prover and verifier, right? Because both of them needs to compute it. And then of course, but this is the prover memories. So this is the prover, okay? So this is what we call it verification code, okay? Call it verification code or attestation code, okay? But of course, your prover has many other things going on in their memory as well. So it has a bunch of different applications, application number 1, application number 2, and so on and so forth, right? And if you remember, I told you when I'm computing the attestation, I want to compute over the entire memory. We want to make sure that nothing in this system has been modified, right? Not this verification code, not this application 1, not this application 2. I want to make sure all of them are correct, okay? So option number 1 is that I go through every content, every line, and I compute the hash of this and then send the hash, right? As long as I can make sure that this indeed has been followed correctly, I'm good to go. And as I said, we're going to use the timing for this. And I'm going to soon I'm going to talk about how the adversary can cheat in this timing and how we can make sure that this timing is indeed correct. But for now, let's assume that this works, okay? And then another strategy that I can do is I basically, all I need to trust in this prover code is this code right here, because this is the one that computes the hash over the entire memory. So if I can trust this, then I can say, okay, I trust you. You go over and compute the hash and whatever you want and send me the results. As long as I trust you, I trust whatever you produce, right? So in other words, it's kind of like similar idea that root of trust that we have for TPMs, right? So in TPMs, we said that I don't trust anything in my computer. I only trust this tiny piece of hardware. And then what we did was we said that, okay, this TPM going to basically compute things on top of each other. And as long as I trust this, then I trust this, then I trust this, and I trust this. And then eventually I trust the entire computer, right? So this idea is the same, but this one is a software-based method. So essentially I'm saying that I'm going to first find a method to trust this verification code. Then this verification code becomes my root of trust. Then everything that this verification does, I'm going to trust. And what this verification going to do is that basically going to go through this content of memory itself and compute the hash. The reason for this is that I don't need to compute the hash over the entire memory anymore. I can just compute the hash over this, compare it with my verifier, and then let the verification code do its own job, whichever it wants to do, like computing a hash and so on and so forth, right? So since I trust that, this is my kind of deputy, this is my kind of ambassador inside that device. They can actually kind of do the trust from that. And of course, I just need to occasionally check whether my verification code can be trusted, because the adversary can change the verification code as well. Does that make sense now? This is what we call a self-checking code. Essentially, the idea is similar to root of trust that we have. Now we have what we call a dynamic root of trust, okay? The dynamic root of trust essentially means that I find a way to trust a piece of code. Then that becomes my DRT, and that DRT then can kind of expand itself, okay? So that's kind of like the idea of this. And then if I go back here, now you see that essentially if I zoom into the verification code itself has the hash function, obviously, some initialization at first, and then some communication for sending the data out. So also receiving and sending, some computation, and some initialization. Once I know that, so once I send the challenge and I compute the hash over myself, so essentially I compute the hash over the verification code using the challenge. Once I know that, I trust that, then I trust the hash function of the application computed by the verification function. So all these other parts is computed by this verification function. And as long as I trust this, I'm going to trust this and trust this and so on and so forth. Okay? Yeah.
It's possible that if the Conversely, has a complete control over the device. They cannot modify the verification, but they can modify the output that is sent by the verification.
True. So the question is, for example, if somehow, for example, the verification computes things correctly, but the moment that it wants to send things out, then values has been changed, what can we do, and so on. We're going to talk about that as well. Yes.
What's the advantage of just making sure or trusting the verification code as opposed to, going through and doing?
Because trusting the verification code can be hand optimized, so you can actually it takes a smaller amount of time. So this delta T becomes much smaller so that it becomes more accurate and more deterministic. Because if I want to go through every part of the memory, then the timings might change because we might have cache misses, or the hash function itself might not be the best hash, the most efficient hash function. But we are kind of decoupling the process of attestation with the process of hashing. That's why it's more beneficial to
So
do
the
it.
noise adds up.
Yes. Any other questions? Cool. All right, so let's actually now talk a little bit about forging and then see how we can actually kind of predict and eliminate this forging. Okay, so if you think about the correct execution of a system, that's the attack-free version of things, is that when I have my verification code and I truly compute the attestation over the verification. Okay. In other words, my program counter and my data pointer, which is kind of the address that I'm really reading the memory from, they are pointing exact same place. That is indeed the verification code, right? So I read it from the verification code, I run the actual verification code, and I'm good to go. Okay. But then there could be three different possibilities of attacks in the system. The first one is that, remember I told you that I can kind of make a copy of this somewhere else. Let's say this part of memory is free. So I copy the verification code somewhere else, okay? And then I change this verification code to what I call a malicious function, a malicious verification code. So for example, these things that you said, like forwarding it to somewhere else and all those tricks that we want to have, essentially this becomes a malicious. So if I change anything in the verification code, it becomes immediately a malicious code. Okay, but in order to pass the test, whenever I want to compute the hash, although I'm kind of running it from here, instead of computing the hash over this content, I'm computing the hash over this content. In other words, my data pointer, my address pointer is pointing to somewhere else in the program. Okay, so that's another option. The third option is that I don't move the verification function. Is that what Andrew was suggesting, is that I change the code in the free zone of my memory, and that becomes my malicious function. And the trick is that instead of running things from the verification functions, I actually running things from that malicious function. The nice thing about this is that I no longer needs to dynamically change the code. Whenever it comes to doing the attestation, I just attestation things regularly. When it comes to this point, then I need to change it. And as I said, this is a self-checking code, which means that I don't even do the attestation for this part just yet. I just do attestation for this part. So the adversary has much easier time to do the attack. And lastly, I can do basically all together. So I can move the malicious function to somewhere else. I can move the verification function to somewhere else as well. So neither my PC nor my DP, the data pointer, is correct. So both of them are at different places. Okay. Does all the three make sense to you? Does anybody? Yeah.
In second and third case, if PC is incorrect, won't the verifier know about it? When they calculate the.
So that's what we want to get at. So we want to show essentially that in order to prevent this, I need to basically both make sure that my DP and PC are indeed the expected value. So it's just reading from the memory is not enough. I need to also enforce that the PC and DP is not different, because either of them can be different and the attacker would be successful, right? So that's the point that we're gonna actually get at. Other questions? All right. So exactly as I said, so essentially, given that there are these potential adversarial scenarios, I need to enforce and make sure that the only thing that is possible to happen is this scenario. Anything else we should be able to detect. How do we detect it? We detect it by reading the content of memory, of course, but also we need to make sure that we always ensure that the PC value and the DP value, or the address, in other words, so DP is the data pointer or the address. So I need to make sure that my PC and my address is also always being checked. Every time that I'm computing something, I need to make sure that the PC and the address is exactly the same. So how can I do that? Essentially, what I'm going to do is I'm gonna add this into my hash computation. So this is the trick that I'm going to use. That I'm gonna, every time that I'm doing something, I'm gonna add the PC, I'm gonna add the address to my address calculation, to my hash computation. I'm gonna explain it first, next. Before jumping into how do we do that, you can also always kind of fall back to the original option of like checking everything, because in that case, all of these things could have been detected anyway, right? It doesn't matter whether your PC is changing or not. Eventually, if I do all of these things, I can find them. As I said, the only thing is there's just some overheads. So there are some advantages of disadvantages of this approach, as I said before. All right, so let's see. So let's see what we want to do. Let's summarize what we have so far. So we want to only kind of like, rely on software, right? And then, as I said, we want to not only just compute the hash, but we want to make sure that the process of hash computations was indeed followed correctly. So I need some evidence that this hash is computed correctly. And not only that, I need to make sure that if the adversary tries to cheat by moving things around or changing the PC or DP or anything else, I can detect it. Okay. And what I found was that I only need to kind of like basically check the verification function, right? That's all I need to know. But in order to make sure that this verification function has not been changed, I need to check basically three things: the content of verification function, the PC, the program counter, and the DP, or in general, the address, okay? So my hash computation function needs to kind of involve all these three together, and that's what we're going to discuss later. And then in addition to that, I'm going to time this process, and I'm going to design this such that if timing isn't like changing anyway, I can detect it easily. Okay? So there are a whole bunch of questions that comes to the mind, and this is the part that you're gonna do in your CA number 4. You're actually gonna like implement kind of something like this in your CA. So there are a few things that you need to think about. Like, for example, what sort of hash do I need to use? Do I need to use a secure hash? Do I need to use an ad hoc hash? Should I use a MAC, which, if you remember, MAC was different than hash. MAC was a process that was using the key, versus hash was just a hash computation. And then the important things about this is that I need to have what we call a time optimal solution, because I want to have something that even if tiny bit of changes can be easily detected. So I need to be kind of like very, very tight in terms of time optimality. And we need to kind of like figure that exact timing, because I want to say that, okay, if this is the threshold that I have in my system, the timing for doing the attack should be much, much larger than this threshold. Otherwise, I cannot detect and I cannot distinguish the difference between attacks and defenses, right? In other words, basically, I need to have a hash computation, or in general, remote attestation protocol, such that my T of attack, okay, is much, much larger than the T of hash computation, okay? But the biggest challenge that I'm facing is we're usually talking about like, IoT systems, Wi-Fi systems, that, it requires like some form of a Wi-Fi connection or or some form of Bluetooth connection or something like that. And what we found is that the time for sending this response is usually significantly larger than any sort of hash computations or any sort of attack calculation, because we're talking about milliseconds or even more for just sending the data. And of course, if this T of sending the data is very large, the attacker can always hide their attack inside this large computation or large delay that we have. Okay, so we need to kind of also fix this problem somehow, that the attack scenario should be somehow much bigger than the hash computation and sending, which is part of the hash computation. Okay. There are also other challenges. Okay. By the way, I'm not going to talk about solutions yet. I'm just giving you some challenges. The second challenge is what we call a proxy attack. Okay, so the idea of the proxy is this: that we are assuming that verifier sends a request to the prover, and the prover going to compute something, and this something is timed, and then it's going to send this to the verifier, and then we're going to say that, oh, if this time is larger than some threshold, we're going to detect it, and this is not trusted. But what if that the prover, instead of computing the hash itself, forwarded to another device called a proxy device? And the difference between this prover and this proxy is that this proxy is much faster device. So let's say, for example, this device is hacking this IoT device. Let's say it's a Raspberry Pi, but since it's controlled completely by the adversary also has a very sophisticated laptop next to them. Okay, so whenever the request comes, instead of actually using the Raspberry Pi to compute, which has much smaller delay, like much larger delays and so on, they immediately forward it to their local PC device that they have. The PC one kind of quickly computes the hash, send it back to the prover, and then the prover can send it back to the verifier, even if they might incur additional overhead because of all this forwarding and all. If this proxy device is significantly faster than this prover device, we're gonna actually can beat this check. Right, so that's the second issue that we're going to have, and we need to fix. We need to fix a proxy. Lastly, there is going to be this additional problem called time of check, time of use attacks, which the idea is if the attack comes and the adversary can quickly remove themselves from the memory, then they can quickly compute the hash and then send the hash, and they pass the test, right? But if they can somehow quickly just at the end of the hash computation, we call it the hook, that they actually can kind of copy back their malicious code right after the attestation ends, then the whole process of attestation doesn't mean it's not going to be useful at all, right? Because the moment that attestation finish, the attackers retake the control and attack the system again. And this is what we call a time of check to time of use attacks, or TUK2, which means that the time we check the system, everything was okay, but when we are actually using the system is compromised again. So we want to kind of like at least make some time between the time we check and the time we use, in other words, to make the system a little bit more secure. And again, I'm going to talk a little bit about the defense mechanisms for all of these things in a little bit. All right. Questions so far? All right, let's have a quick break, and then we're gonna talk in 5 minutes a little bit about the defenses. Okay. So these are the problems that you're seeing in software attestation. One solutions for all of these is what we call continuous attestation. So essentially, the idea is that if I can have a system that basically has, let's say, 2 cores, like one core for regular computation and one core for just doing the prover, then what I can do is that I can do what we call a continuous attestation. That essentially I just send a nonce, do the computation, send another nonce, do a computation. In other words, I'm not letting the adversary to have any other time for doing anything but just doing a computation for the attestation. And of course, this requires you to have multiple cores so that we can actually then use the system for something else. But there is kind of this repeated hashing that could fix some of these problems. But there's a whole bunch of other solutions that I'm going to let you guys see the paper presentations on Wednesday, and then do this computer assignments to kind of learn about how we can do this. Essentially, we can use some form of a timing and see how does the timing can help us in order to make sure that the system is secure. So yeah, do the projects, and then we can revisit this next week, talking about a little bit of software attestation a little bit more. Okay? Questions? All right. So just a summary of software attestation, very versatile, very low overhead. The problem is that since there is no hardware support, there's nothing in the hardware side we can trust, it's achieving security is a little bit difficult because you need to trust on the timing, and this timing may not be actually that robust. Again, once you're doing the CA4, you're going to see that the timing might not be as great as you think it is. And as a result, software attestation, although like it's a good idea and might work in some cases, in many cases may not work, especially because of this T-sand is actually very, very high. And in many cases, we cannot really do anything about this network traffic that we have. This is kind of like outside the control of the IT device. As a result, if this T attack is much, much smaller than this T-sand, then in most cases, you cannot really do anything about this, okay? So as long as, like, for example, part of your CA4, you're going to see that we're going to start adding a little bit of noise to the communication, and you will see that, at some point, no longer your system might work. Even at the beginning, you may not even see that your system works because of the other problems that you may see. But anyway, work on your computer assignments. You'll learn a little bit more, and then we can come back and talk about those things. But let's actually talk a little bit about hybrid attestation mechanisms. The difference between hybrid and pure software is hybrid is kind of in between of a pure software method and a pure hardware method, okay? So it basically says that let's have a little bit of hardware support. Let's have a little bit of hardware trust. Let's see what we can do with that, because that could solve a lot of these problems. So it could solve, for example, the problem of sending the data and all those things, okay? So we're going to talk about like these hardware-based and hybrid method solutions, okay? So the idea of hardware-based is we're going to have, like, first of all, we're going to have two things. First, we're going to have a part of the memory that is read-only, which means that the adversary cannot change anything. And what we're going to do is that we're going to move the verification function and verification code into that read-only part of the memory. In other words, I don't no longer need to protect and make sure that verification code itself is safe. It's always safe, okay? All I need to do is that the process of using verification code to compute the rest of the code, that process I need to kind of develop something for it, okay? The second thing that we're going to have is that we're going to use some form of a key for doing the hash computation, okay? So together, we're going to actually kind of using this hash computation using the key and this verification code, then we're going to fix the issue of attestation that we have in the memory. So basically what has changed is that the attestation code moved to ROM. This, of course, has advantages and disadvantages. The disadvantage is now we need to have a ROM in my system, and the question becomes, what if I don't have a ROM? Many systems do have a ROM, so this is not a big deal. But of course, it's a disadvantage compared to a pure software solution. But the good thing about this is that we are assuming that no one can change anything in the ROM, because once you burn it, you cannot change it. And then the second thing that we are doing is that we are doing a key-based hash function. In other words, we are using MAC instead of using a hash to kind of compute this. The good thing about this is that the adversary cannot kind of cheat in this process, because the secure key can only be accessed by the verification code. And as long as this process is safe, then the computation would be safe as well. All right. So how do we achieve this? As I said, we're using hardware support. Essentially, this is an example of this paper called SMART. This is just one way of doing this. There are many, many other ways Actually, later on, I'm going to talk about the very recent papers that we're going to present recently in NESS in 2024. But like this one, essentially what it does is adding this verification code here and this ROM here. And what it does is that it makes sure that this key can only be accessed from this range. So in other words, you cannot copy the PC, the verification code somewhere else in the program and try to access it from there. It always makes sure that it checks the PC and only allows this key to be read if you are within this range for the memory. In other words, we are not letting the verification code to be moved or to be copied or to be modified. Okay, so all of these things together, and this way we can make sure that the system is safe. If you're definitely interested, you can go and read this paper a little bit and learn a little bit more about this, okay? So there are a whole bunch of concerns, and as I said, I'm going to talk about this kind of like recent papers that we kind of tried to fix this issue. The first issue is we still cannot fix the issue of time of check, time of use attacks. Even if I do this process, what I only can provide with hybrid attestation is that the attestation process itself is safe, but I cannot again guarantee that once the attestation ends, the adversary cannot take over. In other words, what I said, time of check, time of use attacks are not being protected. The second problem is that all of these things assume that the process of attestation is interrupt-free, which means that if I'm kind of computing things, I cannot pause this computation and do something else, because if I do something else during this doing something else, I might go back and change these things that I checked before, right? And if I don't know what I've changed, I cannot trust this. I need to restart the attestation process from the top again, right? So usually this attestation processes, they all assume that you don't interrupt the attestation process. If you do interrupt, you have to start over, okay? You can interrupt the system, but you have to go back and start over. Same thing happens with what we call DMA. For those of you who don't know what is a DMA, DMA is what's called direct memory access. So usually when we have, for example, a memory and a CPU and an I/O sensor, if I want to write something to the memory, the I/O sensor requests to the CPU, and the CPU updates the memory. So for example, if you have a camera that wants to store something, the I/O streams this data to the CPU, and the CPU gets the data and writes it to the memory, okay? But this is like very inefficient in many scenarios that we want to stream data. For example, if you have a camera that you want to store things, there's no reason that you have to go through the CPU and the memory. What you can do instead is that if you have some sort of a channel, a direct channel between your I/O and memory, then you can store things quickly into your memory. This is what we call DMA, or direct memory access, that you have this tiny bit of module here that is still controlled by the CPU. So basically what you do is that through I/O, you first kind of configure your DMA first time. Then afterwards, all you need to do is that you just stream the data in this path. You don't no longer need to go through the CPU, okay? And what is the relevance of DMA in the attestation? Since I/O can directly change memory, again, any sort of DMA behavior needs to be stopped during attestation. Otherwise, you might start checking things and computing the hash. Simultaneously, the DMA might start changing those things, right? And you don't want that, because the adversary might be able to kind of then change things. You want to make sure that if I compute the hash, the kind of the value inside the memory is kind of frozen for at least some time, right? So you want to disable both DMA and interrupts during the attestation process. And again, even if you do that, you still don't know how to fix this time of check, time of use attacks, okay? But still, this is a improvement over the software-only approaches, because software-only approaches, we couldn't have any solutions for communication and all those things. But at least here we make sure that, first of all, the verification code is always trusted, so I don't need to check that. Then I use that to compute the hash over the rest of the memory, like the SRAM and flash. And in order to compute the hash of these, we're going to use the key hash, because the key hash then protects the system from kind of cheating in the process, because you only need to have the key to compute the hash, and the key is only accessible by the verification. That's how we actually fix the issue. All right. And then, of course, if someone tries to access it, what we're gonna do is that we're gonna make sure that nobody but the software attestation code has access to the key. This is the key. This is the software attestation. If anybody else tries to attack the key, basically your memory unit will block that access. Okay. And as I said, I already talked about time of check, time of use. And what I'm going to do next is that I'm going to describe how we fixed this issue. Okay. So far, what I said is that I want to have attestation. I can have a pure software mechanism, but there are multiple problems. The biggest problem was if I just rely on delta T, this is very, very noisy. Okay. It's noisy because of various different reasons, mainly because of the communication. Okay. If the communication required to send and receive data is long, then I cannot really rely on this delta T. Okay. Instead of what I can do is that I can do hybrid. The idea of hybrid is that I trust the verification code because I put it into ROM. I also add a key, and it only allows the key to be accessed by verification code and nothing else. And then the combination of these two means that then I can just compute the results reliably on the device itself. I don't no longer need to rely on the time. I can make sure that whatever hash function that this computes is indeed correct. There is no longer need to send this data to the verifier or check timing. Whatever this value is, hashed value is computed, this is the value that truthfully has been computed there. I can then either like locally or send this over or locally compute it with the expected value. If they match, then we are good to go. Otherwise, we cannot trust the system, right? So that's kind of like the idea of this hybrid method. But hybrid methods has three problems. One is that it has to be uninterrupted, it has to be DMA free, and it cannot really protect us against the 2Q attack. Okay, so these are the three problems that we have with the hybrid methods. All right, so in order to fix that, this is actually what we recently our group has been developed. It's called hybrid attestation with support for interrupt and time of check, time of use. Okay, so let's see how it works. So as I said, if you look at the software attestation, essentially software attestation was this part that we kind of basically verify the content of the verification code, and we were timing it to see that whether the time it takes for doing this verification was smaller than the threshold. So there were two checks that was happening. One is that whether or not the response was correct, and the second is whether the time it takes for computing that response was smaller than the threshold. And as I said, the network limitations is the main challenge there. But the good thing about software attestation was that it has very small overhead. It was very flexible, but of course it wasn't robust. Then we talked about hybrid attestation. The hybrid attestation, the idea was that we have a hardware monitor that basically makes sure that only key and verification code from the specific PC can be used. And what we use is that then the attestation was basically a key attestation, right? And we trust the results. This time we don't no longer needs to trust the time. We only need to check the response. If the response is indeed the expected response, we are good to go because we are trusting this process is being actually, followed correctly. Okay. So there are two problems. One was that this process needs the key and the access, storage. So in other words, every time that we need to compute something, we need to use the key, right? And if you remember, I told you that this means that I cannot do the interrupt because every time that I do the interrupt, I need to basically remove the key. I need to restart the process from the beginning, and that was an issue. So I need to tame, track, and sanitize the key related, and then no supports for DMAs and interrupts. But the good thing about hybrid was it was robust. It can actually fix the issue of software attestation, right? So, and then neither of those two has support with what we call a time of check, time of use attacks, okay? So And then to kind of like show you a graphic of how the time of check, time of use attacks works, essentially if the attacker do the attack before or after the remote attestation, then the remote attestation won't work, because we want to basically know that when we are doing the remote attestation, we can trust the device, so that if device should not be modified after my attestation. If it does, then the process of attestation no longer works. So essentially either hiding before or during or erasing before the attestation, these are all scenarios that we need to prevent in the system, okay? So this is what we're going to propose. So this is how we're going to fix this issue. So essentially, we want to have the flexibility of the software-based method and the security of the hardware-based method. So let's see how we achieve this. And we want to actually eventually wants to get something that can support interrupts and DMA requests as well, okay? So this is what we're going to do. We're going to make this basic observation that during the hash computation, I necessarily don't need the keys, okay, the secret keys. What I can do is that I can do I can do the regular hash computation, but the only thing that I need to do is that I need to make sure that this hash computation itself has not been compromised. In other words, I don't use key in order to make sure that the adversary cannot cheat. I use the monitoring to make sure that the process of hash computation has not been cheated, okay? The good thing about this is that then this allows us to do lots of interesting stuff. And the second thing that we're going to do is that since I'm not sure that whether this hash has been pre-computed or not, or whether the adversary kind of cheating during this process, I can always like use a key at the end of this process to show that indeed this process has been computed correctly. In other words, instead of like every hash computation becomes an HMAC, I'm going to change this to say that every hash computation becomes a regular hash. But during this process, I'm going to monitor to make sure that the hash computation was correct. So it's hash, 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 all the way through the code. And this way I can make sure that the hash computation is correct, is computed correctly. Then if at the end of this process, I know for a fact that this hash computation was correct, then I'm going to sign this. Basically, I'm saying that I trust this hash computation. This is the correct results. So instead of signing every time, which was like the main thing that most of these hybrid computation systems were doing, what we're doing now is we're letting the hash computation to be computed similar way that the software attestation was working. But if this process was indeed correct, then we're going to sign it using an HMAC. Okay, so that's kind of the difference. The signing happens in the end, not during the attestation. Okay, so let's see how we actually do it. And the second thing that we're going to do is that we're going to find the solutions for the time of check, time of use, and I'm going to show you how we actually do that. So essentially, if you think about the properties that we are relaxing, is that so in regular hybrid attestation, we need what we call an atomic execution. In other words, we need to make sure that all the processes are interrupt free. Okay. But once I change this process from using an HMAC to a regular hash, okay, I no longer have any key. So I'm totally fine if this process is reset. Because if, for example, I'm computing this hash and at some point this process has been stopped, I can always say that, okay, I can go back and restart this process without really needing to go through the memory and remove the keys and doing any sanitization or anything, because this is just a regular hash. I can do it as many times as I want, and I can, support interrupts in the middle as well. The difference was that if it was an HMAC, then not only I have to go back, I also have to make sure that the key is not part of this memory. I need to clean up the key from my memory. And that was a very time-consuming process, okay? And then once I can do this for basically once I relax this atomic execution, then I can actually make it flexible for DMA, for reset, and all those things. Essentially, all of them are essentially the same thing, that you were doing the hash computation interrupt free, and now we are allowing to interrupts or to kind of like hiccups to happen. They say that, okay, anything that happens, I can go back again and repeat the process over and over again, okay? And it's still, but you still need to kind of make sure that you have a functional correctness, and then the attacker cannot change the hash functions and all those things. So here's the kind of like the units that you're adding to the system, okay? So we're gonna have this hardware module or HWM, which all it does is making sure that the software attestation process is doing correctly. So remember, I had the software attestation process, which was basically just going through the hash and compute the hash, okay? In software only attestation mechanism, I didn't have any mechanism to make sure that this process was working or not. And that's why we were relying on time. Now what we are suggesting is that let's have a hardware module that basically just check whether the software attestation is following the sequence of the code that it's supposed to. In other words, I'm just checking the DP and PC of this and making sure that the DP and PC does not change. If that's the case, then I'm sure that this software attestation was correct, okay? Then what I'm going to do is that once I know that this process was okay, in other words, my software attestation was okay, then I need to sign this and saying that, okay, I trust this. This is the value that you can get. So we actually sign this and then send this value to the remote user, okay, to the verifier, okay? So that's the difference. The second thing that is different is, so this is the second part. This is the signing part. So this is just for the software attestation. This is for the signing of that, and then this is for sending. The second thing we need to do is we need this controller in order to make sure that if the interrupt or DMA is happening, I need to reset the software attestation process to go from the top and do it again. In other words, I need to make sure that this process is interrupt free. But the difference, as I said before, is if an interrupt happens, all I need to do is that repeat the process from the top. I don't need to kind of clean up the memory, and I don't need to remove the key. That's the big difference. Okay. So for the monitoring, essentially, as I said, I need to check the PC. I need to check the memory address. This is the PC and DP. In order to make sure that my interrupts and my DMA is not happening, I basically check the interrupt request and DMA request. If the DMA request or interrupt request comes, that's the indication that I need to repeat this process. I need to repeat this as much as I need until there is no interrupt during the attestation. Yeah.
But can this like process suffer from starvation if like the
yes, it could. So if interrupts keeps happening, then you're keep repeating this process, and that's a big issue. Actually, we're gonna fix that in a few slides. So we're gonna show you how we can fix that issue further. Questions? All right, so here are the things that I'm going to monitor in this monitoring logic. I'm going to check the DMA request. I'm going to check the interrupt request to make sure that the process is not interrupted. On top of that, I'm going to check the PC. I'm going to check the memory address. The reason for this was those 4 pictures that I showed you that the verification code was moved. If I check these and know exactly where the verification should be, where the address should be, I'm good to go. I don't need to trust anything else. Okay. And so this is basically this part, okay? Essentially, if you think about this, this is a finite state machine that needs to go through basically 4 steps. Initially, start from a monitoring phase, so from the initialization phase, then goes to the monitoring phase, and from the monitoring phase, multiple things can happen. If an interrupt comes, essentially we go to the interrupt and we go back to the process again. Let me actually use a different color. So if you are in the monitoring phase, if an interrupt or an DMA happens, we go to this interrupt state and then go to the end state and then go back. If something happens during the process, so for example, if an attack happens, if the PC is no longer the valid PC, then we go to what we call an invalid state, which essentially says that this hash function is an invalid function, so we don't really trust it anymore. Otherwise, if everything goes well, which means that we follow the attestation process correctly, we naturally go from the monitoring state to the end state. So, and then this is repeated, right? So, for example, let's say there are 16 lines of memory. What you would do is that you keep repeating this. You stay in this monitoring phase until the end. If you know for sure that all the 16 states has been like all the 16 lines has been correctly computed, then you actually sense the correct, like you sign the actual value and you trust the attestation. Does that make sense? Cool. If you're interested, take a look at the algorithm as well. So essentially, this is the software attestation phase, which is essentially just repeating over and over. The software attestation is nothing but what we said before, that takes the nonce, takes the attestation range. It goes through the attestation and computes the hash. The hash function could be like a SHA, could be anything else. And if interrupt happens, it breaks and then repeats this process. If nothing happens, then we just basically get the final value and move on. As I said, the difference here is, so this is basically the hash computation part. The difference is that the whole process is essentially monitored by this hardware monitoring unit. So you have a software attestation mechanism inside a hardware mechanism. That's really the difference that we are basically suggesting. And then once I get the final value, now it's time for signing it. If I trust that this indeed happened correctly, then I'm going to sign it. And this time I'm going to use the key. And the reason that I use the key is that because only then the hardware units can indeed verify the correctness of this approach. If I didn't have the key, then the adversary could have said that, oh yeah, the software attestation works perfectly well. There's no issue with it. But since the key is actually stored inside the hardware, then I'm going to use the HMAC within the hardware units in order to make sure that this process is okay. Okay, so this is kind of this additional kind of step that you need to do, that you monitor the hash computation. If the hash computation is correct, then you sign it. And that's how we actually make sure that this process is secure. All right. So now let's actually talk about the time of check, time of use attacks. Remember, I told you that the problem with the time of check, time of use attack was, so you have your content of memory, you go through it and you say that, okay, this is the hash, okay? The problem is that once you send this, the adversary can go there and change something, right? And this way I can no longer trust the system. So here's the idea that we have. We said that, okay, we can actually monitor memory addresses and PC, okay? So here's what we're gonna do. We're not gonna turn off our hardware module after the attestation. The hardware module keeps looking at the content of the memory. What they're going to do is basically they're gonna answer this binary question that whether the program has been modified since the last attestation. So we do the attestation for the system and let's say we trust it, okay? So now what's gonna happen is that some time takes, let's say a day or 2 days or a week, okay? During this time, either the content of the memory, the program memory, I'm mainly talking about the part that we really care about. We say that whether this content of the memory during this time has been modified or not. If it didn't modify, then you can trust the system because nothing changed in the system. Since you checked it last time, nothing has been changed since then. And this is done by the hardware module, essentially. So since I trust this and I trust this process and trusted last time, I can trust it now. If something changed during that time, then what you can do is that now you know that you need to rerun the attestation. So you no longer can trust the system. You need to rerun the attestation, and this time you will know whether or not you can trust the system, okay? In other words, we basically at least have a flag that tell us whether or not I need to rerun my attestation or I don't need to do this. And an interesting thing about this is this will fix the issue of interrupts, okay? So here's what we're gonna do. So we are doing the attestation, right? We read memory line by line. At some point, an interrupt happens. So we need to stop doing this computation. We run the interrupt, okay? But the interesting thing we can do is that we can say that we can ask the hardware module to look at these lines of memory and see whether during this interrupt, any of these lines of memory has been modified or not. If it hasn't been modified, then there is no reason for us to be worried about, because we already compute the hash of this. We also has a guarantee that they have not been modified. As a result, once the interrupt finishes, I don't need to restart. I can just pick up where I left off, because I have the guarantee that this part has not been modified, so I'm good to go. Yeah.
Interrupts are happening in the device, right? But how is it proven that there are interrupts happening in the device?
So these are all these things are done by the hardware module, which is inside the device. So remember that the hardware module,
In the remote device, right? I mean, it's a very fast.
yes, so hardware module look at the interrupt request. So what we are saying is that if your CPU, so your CPU is sitting here, okay, and this is your hardware module on the same device, okay? So there is this interrupt that going from here to here. If an interrupt happens, then hardware module will know that an interrupt happened, okay? So what we are saying now is that check the addresses during the interrupt, see if any of those addresses is changing something that you were checking before. If nothing nothing changing that, then your hash is secured. Nobody changed that hash. So you can just continue computation of the hash. If it's different, then you go back to the restarting. So if someone changes something in your memory that you hash, then your hash is stale, no longer useful. You go back and restart the process. Yeah.
Can you cause a denial of service by constantly interrupting and changing the first item in memory?
Yes, you can do that. But we are talking about, so we are talking like in the previous scenarios, we had like hash, and then interrupt. And then all those scenarios, they didn't have any idea of what has changed during interrupt. All of them force you to go back and start from the beginning. So even an innocuous, a regular interrupt could cause some form of denial of service. If you had just a system that keeps getting interrupts, you would have had a problem. But here, at least, if your system has a regular interrupt, which is unlikely to change anything from these lines of memory, because this is the verification code, that has nothing to do with the interrupt. So it's unlikely that the interrupt will change anything there. So it's very likely that you do interrupt once, and then you can continue your attestation. All right, so this is how you actually fix the issue of interrupt as well. So in other words, we are kind of allowing this process of you do a hash computation, then you do your interrupt. As long as your interrupt is not changing anything in your hash computation, then you can go back and continue your hash computation. So this is your hash, this is your interrupt. They can actually work they can be kind of aligned together. They can work one after another, or they can be shuffled together. As long as they're not changing. If for example, your interrupt is changing something, then you need to restart the process. But the idea and the basic assumption is that if it's a regular interrupt, it's not going to change anything in your hash function, so you're good to go. We can measure this overhead. The good thing about this is that the overhead for this is significantly lower than having like a full-on hardware module. It only requires a small bit of ROM, a little bit of actual hardware is around like 19% added. This is actually like, if you like compare it with other methods, we show that's indeed this is not significant. The nice thing about this is that your attestation time would be much faster, because first of all, you can allow interrupts to happen. And the second is you are using hashes versus HMAC, and hashes are significantly faster than HMACs, because essentially HMAC is twice slower than a hash, because essentially an HMAC is twice of hash. Like you do a hash of a hash, and that's usually what you get for an HMAC. But anyway, usually like you get twice as fast as an HMAC. And then, yeah, this is the runtime. This is different types of, interrupts and so on. And just to summarize, if it's fixed the issue of tuk2 in a sense that it can allows you to at least know whether your content has been modified or not. As a result of that, this allows for doing interrupts and DMAs as well, because essentially, as long as your DMAs and interrupts does not change the content of your hash, then you're good to go. And another nice thing about this is that you no longer need the key during the hash computation. You can just continue doing your attestation, like a software attestation. You just monitor whether your software attestation is working correctly or not. All right. I guess that's it for attestations. As I said, you're gonna do your CA tour, and there you're gonna see, for example, how you can implement an attack scenario where essentially you have to copy your code somewhere else and then kind of like forward the request to that somewhere. And then we're gonna see whether some form of timing could help us in order to detect this. So that's what we're gonna test. I think it would be very hardware dependent. Maybe in some of your devices, timing may not change at all. For some of you, it might change. That would be actually something that I want to see. And essentially, that's the biggest issue with software attestation, because it's very noise. It's not a very robust solution, unfortunately. Any questions? Cool. Let me also